Okay, so in this lecture, which is lecture 2, we're going to continue with the vector products. So last time we discussed scalar times vector and also vector multiplied by another vector, and there are two different types, one of which was scalar or dot product, and the other one was vector product, or in other words it was called the cross product. So the fourth option is multiplying three vectors, so scalar triple product. Okay, the scalar triple product goes like this. So we have a dot product between vector A and the result of vector B cross C. Okay, so this is a scalar triple product. So I'm going to draw a geometry to describe this. So if this is vector C and this is vector B, now let's think about what B cross C means. So if you write B cross C, then what we're going to do is we're going to multiply B and C and sine theta BC, where theta BC is over here. Okay, that's the angle between vector B and C. And so now the other thing you need to think about is what the meaning of C sine BC. So if you think again, C sine BC is this length. This guy right here is C sine BC. Okay, because it's you're multiplying this length with sine theta BC, you get the height. Okay, that's the y component of that vector C. Okay, so again, this is C sine theta BC. Okay. Yeah, so, but now that you know the height of this thing, these two, this is basically a plane, but now if we think about this, the result of multiplying B, which is this guy right here, with this height, what that results in is a surface area that looks like this, because you're basically multiplying B by C times sine theta BC, right? So you're calculating the surface area shown by this orange color shades. So now we should call this surface area of of the shade. Okay. And now we're going to multiply vector A, which is this guy here, that's A, okay? And it's not perpendicular, but it's, you know, it's still pointing towards the upper side compared to this 2D plane formed by vector B and C. Now if you do an inner product of that, oh, by the way, I forgot to write that normal vector AN right here, because the result of the cross product is a vector normal to the 2D plane. So this is the normal vector direction. So this is BC sine theta VC AN normal. Okay, that's perpendicular to that 2D surface formed by vector B and C. So if you do an inner product of A with this new green vector, which is a result of B cross C, then essentially what we're doing is we are multiplying A, right? And we're multiplying the magnitude of the result of the B times B cross C, right? So it'll be BC sine theta BC times cosine, let's call this, I'll call this theta, I'll just call this pi. Okay, let's call this angle pi. And you can see that A cosine pi is the length shown here. So if you think about A cosine pi, oops, it's this length here. If I zoom in, this is A cosine pi, this guy right here. Okay, that's A cosine pi. Okay, so it's a vertical component to this 2D plane formed by B and C. So what this is going to be is a 3D volume, because now A times cosine theta is the height. So these two guys are the height. And these guys right here are the surface area. Okay, BC sine theta BC was the surface area, right, as discussed earlier. So it's surface area times height. So the whole thing is a volume. The result is a volume. Okay. So essentially, you can imagine that this is going to be a volume that looks like this. Okay. Um, yeah, so I think that's it. So the scalar triple product results in a volume. When it comes to this scalar triple product, permutation is possible. So these are just mathematical properties, but sometimes it could be useful in solving electromagnetic problems. So let's talk about it. So the basic form was A dot B cross C. Okay. But that is equal to B dot C cross A. And that is equal to C dot A cross B. Okay, the reason is because we utilized the 2D surface formed by vector C and B in this drawing, but there are other ways to do the calculation of volume. Okay, in order to calculate a volume, you can utilize the side walls instead of the bottom wall, and there are other side walls that you can use formed by C vector and A vector, and also A vector and B vector. Okay, so the resulting volume quantity will be exactly the same. However, if you do this, let's say A and in another case, if you do basically you swap the location of vector C. So instead of B cross C, you're doing C cross B. Then, as discussed earlier, because of the right-hand rule, the direction of the normal vector resulting from this switch in the vector location in the cross product will result in a minus sign. So that would be a minus the whole thing. Okay? Because as we know, these two have this kind of correlation. Okay? So again, if you have B and C like that, and you apply the right-hand rule, meaning that you're going to grab with your right hand from B to C, because B cross C, then you have the vector pointing upwards because that's where your thumb is going to go to, right? But if you grab in the opposite direction, if you go to the other direction this way, okay, I should use a different color. But if you go C to B, then your normal vector will point downwards like that. Okay, if you grab it from C to B, your thumb points downward. Yeah, so that's the fourth property for the fourth type of vector multiplication that you can utilize, and there's a last one. So the last one is the fifth one is called vector triple product. Instead of scalar triple product, we're going to call it vector triple product. Um, and this is something that looks like this. You do A cross B cross C, that is equal to B A dot C minus C A dot B. Okay, so if you do a dot product between two vectors, the result is a scalar value. So these guys, this and this, these are scalar. Oops. Scalar. And if you multiply a scalar to a vector, it's just, you're just changing the magnitude of basically B and C. Okay, so that's the result. But yeah, there could be an example that we solve together that would utilize the vector triple product, but I will leave it there. So this is the vector triple product, and this is a scalar triple product. Now you might be wondering, what about the division by a vector? Okay, what about division? Okay, so what about vector division? So for instance, vector division can look something like this. Okay, scalar divided by a vector, K over A. Okay, or something like vector B divided by vector A. Okay, those are the things we can think about. But these are meaningless. There is no defined, there isn't any definition for vector division. Okay, so division, by a vector is undefined. Okay, so it's basically meaningless. And we won't solve any problems that involves vector division. Okay. All right. So we're going to now talk about the coordinate systems, and we're going to work on orthogonal coordinate systems. So let me write that down. Okay, orthogonal coordinate systems. So what this means is a point in 3D space is described by three mutually perpendicular surfaces. Okay, it may not be, these surfaces may not be planes. Okay, these surfaces may not be planes. Okay, it could be a curved thing, basically. But they are still perpendicular to each other. So, so we call this, we express the three mutually perpendicular surfaces using base vectors. Okay, so we call this AN1, AN2, AN3. These are called base vectors. Okay, so among the orthogonal coordinate systems, we are going to study Cartesian coordinates and cylindrical coordinates and spherical coordinates. And these, some of them will be easier to deal with depending on the geometry of the problem that you're tackling. But before we move on, let me just show you the properties of the base vector. So these guys, AN1, AN2, and AN3 are orthogonal, meaning that if you do a cross product, let's say if you do AN1 cross AN2, that would become AN3. Okay, let me put that hat. And similarly, if you do AN2 cross AN3, that becomes AN1. Okay, and lastly, AN3 cross AN1 becomes AN2. Okay, and obviously these are unit vectors, meaning that the length of these guys are 1. So if you do a multiplication of itself, for example, if you do AN1 inner dot product of AN1, that's essentially 1 times 1 cosine 0, so that becomes 1. Okay, but if you do an inner product of any other base vector, so if you, for instance, do AN1 inner product or dot product AN2, that becomes 1 times 1 times cosine 90 degrees, because AN1 and AN2 are orthogonal. Okay, so since cosine 90 is 0, this whole thing would be 0. And the same thing applies to AN2, AN3. That would also be 1 times 1 times cosine 90. So that'll be also 0. Okay, so unless you multiply by yourself, which will lead to 1, if you multiply with other base vectors, because they are all 90 degrees, okay, their angles are all 90 degrees, that's the definition of being orthogonal, that will result in 0. So using this base vectors, now you can construct your own vector. For example, let's call vector A is A1, AN1 plus A2, AN2 plus A3, AN3. Okay, we can call it like this. So that means if we just assume that if we put this on a coordinate system, and let's just assume that AN1 is this direction, AN2 is this direction, AN3 is this direction. Okay, in that case, the resulting vector A can be something like this, where you have the AN1 direction in the amount of A1 and AN2 direction in the amount of A2, and then the third, that direction, AN3 direction, being A3. Okay, so that's the height. So if you combine these base vectors, and if you plot it, then you can create any vector such as the one shown by this pink arrow. Okay, now we're going to move on to Cartesian, cylindrical, and spherical coordinates. So number 1. Cartesian coordinates. Okay, so Cartesian coordinate is the most, I would say, general coordinate systems, which is an XYZ coordinate systems. So the base vectors are essentially marked in XYZ. Not base vectors, but all vectors. So the coordinate systems are XYZ coordinates, and of course the base vectors are AX, AY, and AZ. Okay, and because AX and Y and Z and X, these are all orthogonal, the properties that we discussed just earlier applies. So if we do a cross product of AX and AY, that leads to AZ. Okay, and if you do that AY cross AZ, that leads to AX. And if you do a AZ cross AX, then that leads to AY. Okay, so what I would recommend you do is draw this. Let's just do it together. Let's draw this. And let's call this X, Y, and Z. If you apply the right hand rule, so if you grab from X and end at Y, your thumb will be pointing towards the Z direction. Okay, that's why we have this first equation. And if we do the same with Y and Z, if you grab Y and end at Z, the normal vector will be this cyan color. Okay, and if you grab the Z and end at X, then you will now have this maroon color pointing towards the Y direction. Okay, maybe it's a brown color. But now you can see how the right hand rule is applied visually. And so if we're going to express any vector in this Cartesian coordinate system, so let's say you're going to have vector A, and it's going to be AX, AX, like this, and AB, AY, sorry, AY, AY plus AZ, lowercase az. Okay, so again, these guys are all scalar. Okay, and these guys are all unit vectors. Or we call it in this case base vectors. Okay, the base vectors is a unit vectors can become base vectors if they are orthogonal to each other. Okay, so that's how you express vector A. Similarly, vector B would be bx, it has to be ax. Okay, the base vector doesn't change. by, ay, bz, az. Okay, similarly, bx, by, bz, these are the scalar, and ax, ay, az, these are the base vectors. Okay, they, regardless of the vector, base vectors are all the same. They're all ax, ay, and az. So how are we going to do the inner product, okay, or the dot product? So somebody asked me today, in the last meeting, are we going to cover vector component multiplication? Okay, so this was a b cosine theta AB. Right? This is one way of expressing it. Okay? But in case you already know the x, y, and z component of a vector in this scenario, we can also calculate a dot b in this way. So that would be ax plus AY, AY, AZ, AZ, like that. And we're gonna do the same for B. BX, AX, BY, AY, BZ, AZ. Okay. Let me just move this over. It'll be like that. And the result will simply be multiplying like this, multiplying like this, multiplying like this. Okay, so in other words, the result is AX, BX, AX dot AX and plus AY, BY, AY dot AY plus AZ, BZ, AZ dot AZ. Okay, so as we discussed, these guys are all 1 because these guys are all 1 plus 1 multiplied by 1 cosine 0 degrees, so that is 1. Okay, that's all 1. So you will see that this boils down to AX, BX, AY, BY, AZ, BZ. Okay, and you can see that these are all just scalar. So this is a scalar result. So you can see that as you already know, the dot product of two vectors results in a scalar. And component-wise, it's showing us the same thing. And the most important thing is, regardless of how you do the calculation, either this way or either this way, the two results should be equal. Okay, they are equal. You might be wondering, so the way I did the multiplication, this is not a formula. Actually, you would have had to multiply, for example, this guy with not only the first one, but also the second one, and also the third one. And same thing for the rest, okay? But except for the case where you are multiplying the lowercase ax, which is one of the base vectors, by itself. For example, if you look at the second product, which results in ax, by, and ay, okay? This results in 0 because of ax multiplied by ay, right? Ax dot ay. That becomes 1 times 1 times cosine 90 degrees, so that's 0, right? So this whole thing goes to 0. That's why we don't see those left. Okay, the same thing with the rest. So because ax, ay, and az, these base vectors, these lowercase ax, ay, and az, these are all orthogonal to each other, they all go to 0 if they're multiplied, unless they're all multiplied by themselves. Okay, so that was the dot product. And if we do the cross product, last time we learned that it's A times B sine theta AB times the normal vector. Okay, you gotta make sure you put the normal vector in there. Okay, this is the normal vector. But if you know the vector component, so we already know that what A and B vector looks like. In that case, this is how you do it. So you put AX, AY, AZ, and then you put the components, the magnitude components of it, in BX, BY, BZ, right? So this is basically vector A and vector V. Okay, but you just arrange it in this way, and the top is the base vector. And then what you do is you first of all you swipe out the first row and the first column. Okay, and then you multiply AY, so and then you do a cross like this. Okay, multiplication wise. So you'll do AY times BZ minus AZ times BY. Okay, that's one. The other thing you need to do is you need to move this screen and wipe out the first row and the second column. And you need to do the X multiplication between these guys. Okay? The ones that that survived, they're not wiped out by this green highlight. Okay? But the easy way of doing this is by putting AX and BX over here, and then do the cross multiplication. So in this case it'll be AZ BX minus AX BZ. Okay, so that's the second chunk. Now the third chunk. The third, I'm going to erase this. The third we're going to wipe out the first row and the last column. And we're going to do the cross multiplication using those guys. So it'll be AXBY minus AY BX. Okay, so that's the third scalar that results. And the unit vector still survives, so this would be AX. These guys are all hatted. And this is AY. And this is AZ. Okay, and you add all of them together. Okay. So now you'll know that the cross product results in a vector. So this is a vector. The result is a vector. Cross product result is a vector, normal to the plane formed by vector A and B. Okay, so again, if vector A is like this and B is like this, A and B, then you have a normal vector. Then you have AB sine theta AB with the normal vector AN. So this is normal to this and also normal to this. Okay, and this expression is this. So you'll notice that these guys, these guys are all scalar. Okay, these guys are all scalar. Multiplied by the unit vectors, the base vectors. This guy, and this guy are the base vectors. So the total result of A cross B is still a vector. Okay. So that's how you do it. All right, so just email me if you have any questions about this, or if I made any mistakes, let me know. Yeah. So now we're going to talk about differential length. Okay, so this is a very important concept. So differential length. Differential length. So what does this mean? So if you have a line, not a straight line, just a random line, any line, that goes like this in XYZ coordinate. Okay. Then we can express this line by segmenting it. So by cutting this in a very small bit, like very tiny bit of this length. This is called DL. We're going to call this DL. Okay, this little piece of wire. And the expression for DL will consist of three components, right? Because in this case, we have AX and AY and AZ as the three base components. Three base vectors. So there will be a little increment in the x direction. We call this dx. Okay, so this is a tiny amount in the x direction. That has to be multiplied by ax because that's the x-axis contribution. And there will be a y contribution too. So dy, a tiny bit in the y direction, multiplied by ay, and dz, tiny bit in the z direction, multiplied by unit vector az. Okay, so this is how you express this arbitrary line. That's the differential length. We are going to utilize this to do some integration along the line, okay, later, probably in the next chapter, or maybe also in this chapter. There's a differential surface area. If there's a length, there's a surface area. So now we're going to talk about differential surface area. So in this case, again, also in XYZ coordinate system, now let's say we have some kind of surface, okay? I don't know how to draw this artistically, but let's say there is some kind of a surface, okay? And this has, let's call this ds because it's a surface, tiny amount of surface, ds. Okay, so wait a second, let me redo this. So a surface is represented by the normal vector, which means the vector coming out from this surface. So if you zoom in, there's this normal vector coming out like that. So if this is a surface, that's the normal vector, and we can call this dsy because it's a tiny piece of surface in the y direction, and the amount would be basically dx times dz. Okay, because now we have this part is dx, and this part is dz. Okay, so the surface area itself pointing towards where its normal vector is pointing towards the y-axis is defined by dx times dz. Okay, if you have a surface that looks like this, then you have dx over here and dy over there for the surface dsz. So dsz would be dy dx. Okay, and similarly, if you have a surface that looks like this, where the vector is pointing along the x-axis direction, that'll be dx, and the resulting length would be dz, and that's dy and dz. So this guy would be dy dz. Okay. Also, this is going to be very useful in calculating electric fields and quantifying the amount of charged clouds enclosed in a 3D like a bubble. Okay, we will utilize this more when we talk about Gauss's law in the future. All right. So the last thing is differential volume. Okay, differential volume. Okay, volume. So differential volume is basically, again, XYZ coordinates. It is a tiny cube that has a volume, a tiny volume dV. But if you look at the component of this, it is dx, dy, dz. Okay? So the way you express dV is dx, dy, dz. Okay, tiny amount of x and tiny amount of y and tiny amount of z results in a tiny volume. So this is a definition of a differential volume. Okay, so that's the end of the Cartesian coordinates, and we're going to now move on to cylindrical coordinates. Cartesian. Okay. Number 2. Okay, cylindrical coordinates. it utilizes r comma pi comma z. Okay, the way it looks is like this. So if you have xyz, okay, you have an r. First you have an r. Okay, you have an r. So the radius stays on the xy plane. Okay, and the radius is r. So this is r. And the location of the r is confirmed by this angle. The angle that starts from the x-axis to where the r vector ends. I mean, where it stops. So that's the pi angle. And the last thing is z. So you can go up by the amount of z. Okay, you can see. So that would be your point described. But overall, it's a coordinate system. I mean, it's a cylindrical coordinates because if you spin this around, it'll be a cylindrical shape. Okay, like this. Okay, that's why it's called the cylindrical system, cylindrical coordinates. Okay, so because this is also a orthogonal coordinate system, although it's not Cartesian, cylindrical coordinates are also orthogonal. So the base vectors are AR, A pi, and AZ. Okay, these are the three base vectors. And because they're orthogonal, if you do the cross product, that ends up being the remaining ones. That become A pi. Okay? And the reason is because if you look at this point, let's go back to this point where we ended up. And if we draw it, so the AZ would be from this point, okay, AZ will be pointing this way, and AR will be pointing this way, and a theta would be tangential to this circular path, and this would be A pi. Okay? So it's easy to see that AZ is perpendicular to both A pi and AR, but it could be a little difficult to understand why AR and A pi are perpendicular. And the reason is because if you look this from the top down, then the way it looks like is you will see y-axis and an x-axis, and you will see a circle. You'll see a circle like this. Okay, if you look at from the top down view. And the r vector is essentially going to look like this. So AR is over here, and the tangent of this circle is A pi. Okay, so if you think about a tangent vector on a circular path versus the radius, this is definitely orthogonal. So although it's a slightly different coordinate, cylindrical coordinate, all the base vector, they're all orthogonal, just like in the Cartesian coordinates. So similarly, if you to express a random, vector A, that would be AR, AZ, and B would be BR, B pi, A pi, AZ. Okay, you should note that the base vectors are the same regardless of the vector. And so if you do the dot product and the cross product, let's first do the dot product. Okay, the dot product is the same thing, right? If you do A dot B, then essentially we're going to multiply all of these, but except for these multiplications, okay, where you just multiply AR to AR, if you do this multiplication, the green lines will result in 0 because AR and A pi are orthogonal, and AR and AZ are orthogonal. So these are going to end up being 0 because of cosine 90 degrees. So what ends up being is AR/BR, and of course we're going to do AR and AR, but these are 1, right? So similarly, we'll end up getting A pi and B pi plus AZ BZ. Okay, so that would be that would be the result of dot product. For a cross product, same thing. If you know your base vectors, and if you need to do a cross product, again, I will put AR, A pi, and AZ, and put the AR, A pi, and AZ and BR, B pi, and BZ. Okay? And I'll go and do these multiplications throughout, and the result would look very similar. So that would be AR and plus um like that. The last component would be AR Okay, so you can see now again that these values are all scalar, and the highlighted, these are all vector, and the overall result is a vector. Okay. Let's talk about the differential length and differential surface area and differential volume. And I will stop the recording after that. So the differential length. Okay, DL. So how are we going to express DL using the cylindrical coordinate systems? So let me give you the answer. So first of all, it's going to be the small increment, small length of dr in the radius direction multiplied by the unit vector in that direction. And strangely, it's not just purely d pi, a pi, you would think this would be it, and plus dz and az, you would think that this would be the differential length. But the important thing is that you need to multiply r over here. So this is a key here, very important. Okay, the reason why we do this is because d pi, this guy, this is not a length. Okay, this guy is not a length. Okay, it's not a length alone, it's an angle, right? It's an angle. Okay, so if you think about the arch length of a pizza, and the pizza's radius, the angle is pi. Now let's call this d pi, small pizza, and the radius is r. Okay, then the way you calculate this length here the arch length. This is r d pi. Okay, r times the angle results in the arc length. So similarly, because of that reason, we need to multiply r. Okay, because you can see that this guy is just dr because it's already a length. dz is already a length, so you don't have to multiply anything. But d pi is an angle, so we need to multiply r to represent a small portion tangent to the outer surface of this arc. This could be confusing, so let me know if you want me to repeat that later. Yeah, so similarly, differential surface, okay, differential surface. ds, there will be a dsr component, which will be a multiplication of r d pi and dz. Okay, again, remember this r is multiplied by d pi to represent the length. So now you can see that this is a length and a length becomes a surface, right? Length multiplied by length. Similarly, ds pi is dr dz, and sz is r d pi and dr. Okay, these are the three differential surfaces. And lastly, the differential voltage. I mean, not voltage, volume. dV is r d pi dr, right, and dz, right? So again, make sure you keep this r. Okay, so this guy is a length, this multiplication is a length, and this is a length. So that's why it leads to a volume. Okay, so I will stop the recording here, and next time when we meet, I'll take questions because this can be a little bit confusing. So I'm happy to go over it again. And if there's no questions, we'll continue with the conversion of a vector from cylindrical to Cartesian coordinates. Okay, thank you everyone.